All right, so welcome everyone for today's coaching seminar. It's my great pleasure to introduce Shaoshi Chen from Chinese Academy of Sciences, and he'll speak about stability problems in symbolic integration.
Thanks, Ronnie, for the introduction, and also thanks Alice and Gleb and Michael organizing this coaching seminar. I think the last time I was giving talk at this seminar is 4 years ago. So it's my great honor to give my third coaching seminar talks. So today I'm going to talk about my recent work, which is connecting some dynamical system and symbolic integration. So let me start from symbolic integration. I think in coaching seminar, I don't need to sure I have slides for defining differential field, but anyway, so let me first give a brief introduction to what are called symbolic integration. So this starts from integration problem. So integration problem split into two parts. One is about indefinite integration. So definitely, actually, this is involves no limits. So for a given function, we would like to find another function in the same class usually, such that the derivative of g is equal to given function f. Basically, this indefinite integration can be formulated, and we will see in differential algebra. So, and for example, if f is log x, then we can get the antiderivative g is of this form. So, and problem to computing finding indefinite integral is for the definite integration. So definite integration is has geometric meaning. So you have a function which is continuous, need some analytical condition like continuous in the interval, and then we can consider the integral for over this interval. And in order to compute this definite integral, so the idea in calculus is to find the antiderivatives. For instance, if you want to compute the integral from 1 to 2 of log x, then you can use this the primitive or antiderivative to evaluate this integrals. And this is actually the fundamental theorem of calculus, which build the connection between the indefinite integration and definite integration. So once you have an antiderivative of the given function f, then you can evaluate this definite integral, which is equal to you're evaluating the antiderivative at the two endpoint. So this is somehow this is called classical Newton-Leibniz formula, which reduce the definite integration to indefinite integration. But the life is not always like this, because for some example, you cannot find a very nice antiderivatives, then this direction will not work. For this example, for log x, we find the antiderivatives, which is also has very nice form. And then you can evaluate this definite integral nicely. But how about this one? We know in calculus, you cannot find the indefinite integral of this exponential 1 over x squared is not elementary function. So we will specify what is elementary function in the next slide. So, which is usually we call the closed form or nice form or some explicit form. But first, let me give a very informal definition of what is elementary functions. So we start from some constant and a variable x. So now we're talking about the univariate elementary function. You can also talk about several variables, but let's say we fix the univariate case. And then for those variables, you can do the usual operation. And then you can get a field of the rational functions. And after getting the rational functions, you can take the exponential of the previous already built functions, and then you can iterate this process. So for informally, usually in calculus, we will define the elementary function in the following way. Say, elementary function is a function of x, which is the composition of a finite number of following operations. You can use the binary operation, like if you have some elementary function, you can take the sum, difference, product, or quotient. And then you can also apply the unitary operation to the function which you have already obtained in the previous steps, like taking the exponentials, logarithms, and also you can also solving a polynomial equation, which is called the algebraic extension. And for instance, you have you use the constant 3, 3, 1, and you can use the variable x. You can build this polynomial which use the addition, multiplication, and then you can also take the quotient of this, like division, and then you can also solve the polynomial equations. You get this root of this, and also you take the exponential, so you can iterate this process to get the more and more complicated or more and more general element functions. This is the feeling we get. What's the meaning of element function in calculus? Or you can get more. Now let me put everything in the framework of a differential algebra, which is make this feeling more concrete or more algebraic. So we first need to define the differential ring and differential field. So this is like a ring. We suppose people all know that let R be an integral domain, and then a differential ring actually is a ring together with this kind of a special operator or map. This is the additive map such that they satisfy the following the Leibniz rules. So this is called a derivation on this ring, and then the pair is called a differential ring. And if this ring is a field, then we call this a differential field. So as I said in coaching seminar, I should skip these slides, but anyway, let's keep everything elementary. So for polynomial ring, so you can equip this ring using the usual derivation. So then this becomes a differential ring. And also for rational function field, you can also use the usual derivation. And then sure, you can define other kind of derivation, but this is the standard way to define the derivation. And also for more general, like for algebraic extension, finite algebraic extension, you can also define this is the minimum polynomial satisfied by this algebraic function. Then there is a formula which help you to evaluate the derivative of this algebraic function uniquely. So this way actually is the derivative of alpha actually is uniquely determined by the minimum polynomial. And also you can define the transcendental extension when you have adding this exponential, and then you can also differentiate using the Leibniz rule. So in this way, we can turn an elementary function, the field of all element function, into a differential field by using this derivation rule. And more general, you have like in algebra in the field theory, we have a field extension, and then you can also have a lot of you can extend the derivation from the small field to a bigger field. And this is exactly the so-called differential extension. This is very natural definition, just the usual field extension, but you should also extend the derivation. When derivation restricted to the smaller ring, then it's become the derivation on the smaller ring. Then this is the differential extension of the differential ring R. And then we have once we have this differential ring extension, then now we can specify what we mean elementary extension. So this is let F be a differential extension of E. For maybe I just avoiding the complete the star, so I just use the same symbol for the derivation D. And an element T from the bigger field is elementary over the smaller field E if the following three conditions holds. So either T is the algebraic over the smaller field, or T actually, because here you in the differential field, the only operation you have is derivation. So you take the derivation of T, and then take the quotient of divided by T. then this is, if this is equal to the derivative of another element u, which is from the smaller field, then we say t is exponential over the e. But sure, if formally, symbolically, you can write e equal to exponential u. But you know, this is just a symbol. It's not the meaning actually is here. So also similarly for logarithm, so the derivative of t from the bigger field is equal to the logarithm derivative of another element from the smaller field u. So this is we write t is the logarithm of u. So this we call, then we say t is logarithm over e. So elementary is one of them. So this is then now we have the, for instance, let's take the rational function field, and then the usual log is the logarithm elementary over the rational function field. And then we can define the elementary. Once we have the elementary extension, then we can define the what we call the elementary functions. So element function. So a function is elementary. Usually we say over the rational function field. If there exists a differential field extension f, which is you joined this rational function field iteratively by elementary elements, which means ti is elementary over the previous field, no, the field generated by the previous elements, t1 to ti minus 1 for all I. So then one element of this field is called elementary over the cx. Sorry, here I omitted the over cx. Usually when we say elementary function, usually we mean elementary over rational function field.
And I guess so, you mean that fx is in the field f, right?
In the field f.
Right.
Is any element of this field is called elementary over cx.
Yeah. But I'm saying here in your definition, you meant to also write that f needs to be in f. Is that correct?
Oh, sure. Just there exists a differential field extension which includes f, the small f, and then we say, right, you're right. Here I should say here at the such that and somewhere such that f in the big f. Yes.
Thank you.
Let's take the previous example. So this is we have the feeling that this is must be an elementary function. But now let's see what's really the t1 to tn is. Here actually we can build this the field which include this element function. T1 actually is the algebraic function. So this is T1 is elementary over Cx because it is algebraic, and the T2 is exponential of T1. So T2 is also elementary over the Cx T1, and T3 is log of T2, and so this is T3 is elementary over the previous field, and T4 is algebraic over the previous field. And then you can see that F1 actually is equal to the pi over this term, and then Fx is elementary, is in this field, and is because pi is in the C, so we have, then we can show that indeed this is an element function. This is the still in symbolic integration. There is actually still a mysterious problem for a given expression, and how you can write down the T1, T2, T3 in a very economical way to show that this indeed element. This is not a very here you can see, but actually in general it's more complicated. So okay, now we have the idea of what is the elementary function. Now we can state what is the symbolic integration. So let E be a f and be two differential field, and f is the differential extension of E. Now the general problem of symbolic integration following: given a function by given, which means usually you given the specified E, and then you have a function in this field, and then you want to decide whether there exists another element f in f. F is the extension. Usually f is the extension of the given integrand, such that you have this. So G is the antiderivative of f. So in symbolic computation, usually you need to specify what E and F are. And then if such kind of G exists, then f is integrable in F. So suppose, for instance, if f is the field of element function, then an element function has elementary antiderivative, then we say this is elementary integrable. So as already said, elementary integration problem, we focus on the elementary input. So when fx is in an elementary function field, a differential field, then we usually curious about whether the indefinite integral of given elementary function is still elementary or not. This is the very classical question. Actually, maybe at the beginning of the calculus, mathematicians already think about this. So, and in our calculus textbook, usually the teacher will tell you the following integrals are not elementary function, and usually will not give you the proof, just ask you to accept the fact, like exponential x2 and 1 over log x and sine x over x, and this is the elliptical integrals, and this is also not an elementary function. And the key to show those so maybe let's just give a very brief, because I think this is there are some books about on the symbolic integration. I just show you, so I will not go through the detail because I prepared maybe it's for 1 hour slides, but I will skip some steps. So in the slides, I think you will see that how the topic of symbolic integration developed. So the first period is the theoretical development, which is starting from the Abel's very classical paper on elliptical integrals, and then end with the I will not go through all this, and end with the Ritter's very nice little book on integration in finite terms. I think still this is a very nice book for introducing this topic. Up to here, and then the symbolic integration has the algebraic foundation, and then we can start think about how we can really do the computation. Because if everything is formulated in algebraic terms, then we can think about to have an algebraic algorithm, and also more efficient way to do integration. And this is also start from when we have a computer, and the first project for actually this is all the first project for artificial intelligence. So this in MIT, there is a group who think about how we can use the computer to do the freshman's the calculus problem in freshman's calculus, the integration problem in freshman calculus. And this is almost the beginning of the artificial intelligence, also the beginning of symbolic integration. And then everything developed. So especially I should point out that there's one very nice few papers, I think 3 papers by Rosenlich introducing this topic. And also there's some other algorithmic developments in this topic. And this is the Davenport's PhD dissertation. And also the Trigger's dissertation. And Michael and his co-authors has also extended the Lewisian theorem. We will see Lewisian theorem, which play a very crucial role in symbolic integration. And this also develop this keep developing in symbolic integration community. So there are a lot of works in this topic. I will not list all. And recently, there's also a nice thing is about the number theory problem, which are arising from elementary integration, initiated by the Umberto Zannier. Has a lot of paper. I think he has a series paper with David Master on this topic. So with Zimi, we also have some works on this. Especially last year, I think they have finally finished this long paper about this building the elementary integration and some number theory problems. I think it's a very interesting paper to read, to see how this connect to number theory problem. Okay, this is the probably I make a joke with Zimi. Each time I give a talk on symbolic integration, I usually have no time for presenting new results. So probably now I should now we will see some new results. So the classical foundation or the foundation for symbolic integration is the following theorem, which is due to Lewisian. It's called the Liouville theorem. This characterizes which kind of element function has elementary integral. So if f is an element function, if the antiderivative of f is still elementary, then this antiderivative has very, very special form. So it's this following form, has two parts. The first part, G0, is already in the f, in the field which f lies. And then there is a linear combination with constant coefficients of log of the GI. GI and G0 are already in the field which f lies. So which means if this is elementary integral, then the integral is very, very, in certain sense, very simple. You don't need really to do a lot of elementary extension of the f. And with this theorem, actually, Liouville managed to prove the following three functions is not elementary. So because if it's elementary, you prove by contradiction, then then you lead to some contradiction. And there's two classical theorem in this. This is very classical. One of the theorem is due to Liouville, but also presented, explained in Hardy's book. Hardy had written a book, also had written a book on elementary integration. I think it's also very nice book. This book, I forget, it's 1916, almost 100 years ago or so. And in this book, he stated the following very neat result. So if f is any rational function and f log x is elementary integrable, which means the antiderivative of this function is elementary, then the f must be of the following very special form. F is equal to sum of derivative of another rational function and a constant divided by x. So this is the f must be of this form. Otherwise, so this implies that sorry, log x divided by x minus 1 is not elementary integrable. So, but the log is divided by x, like f, then is still elementary. And the second classical theorem is the Liouville theorem on the integration of exponential functions. So fg, both are rational function. And if this is elementary integrable, if and only if f and g satisfy the following equation, which is so-called Riche's equation. So for here, the h is a rational function, which means this first order differential equation with coefficient f and g prime has the rational solution. So this actually is the use this result, we can prove that the exponential x to the power 2 is not elementary integrable. Let me skip, just come to here, because by the Liouville theorem, if this is elementary integrable, then here f is 1, g is 2x, and here so this equation must has a rational solution. But then you can argue that this has no rational, because if there is a rational solution, and then if you can show that this rational function must be a polynomial. If there is a some denominator, then because derivative will increase the multiplicity, and f will keep the multiplicity, so they cannot cancel out with to 1, and then f must be a polynomial. But if it's polynomial, you can also cannot get the solution. So this is like an exercise for, you can show that this has no rational solution. Then you prove that this is not elementary integrable. But you need a Liouville theorem to reduce problem to this equation for solving the rational solution of this equation. Okay, that's almost I have finished the presentation about the symbolic integration. Now let me come to the stability problem. So actually, think about the stability problems. I'm motivated by reading some books about transcendental numbers. I think I read a lot of paper about how to prove pi is irrational numbers. And I observe that for most of, I will not go to the proof because you can. And I found out, I observed that they usually start from certain kind of indefinite integrals. And in this integral, the integrand is always like some trigonomic function, like sine, cosine, or something, and then multiplied by some power of polynomials. And I was curious, and when you try to derive the recurrence, and you observe that actually the integrand, when you integrate once, you get the antiderivatives, and you can still integrate again. And somehow this is this kind of form of the function, you can integrate infinite times, still get the elementary function. Actually, you get the cosine, sine, and sine cosine like this. And then I was curious about which kind of a function you can integrate. Sure, you can guess that the polynomial definitely is in this sense is stable, and the sine, cosine definitely, and exponential is also, and log, you need a little bit to check whether log x is, you can integrate infinite times, you still get the elementary function. So this is roughly an idea of the stability problem. So, but I need to put this kind of field idea in more formal way. This is we need some terminology from dynamical systems. And a discrete dynamic system is just a pair, and where x is any set, you can take any set, and phi is the self map on x. So this is a very general setting for discrete dynamic systems. But there's even this very simple definition. Actually, there's 4 types of sets. It's very crucial to understand this dynamic system. The first one definitely we know is called a fixed point. We were curious about which kind of elements of the set x is fixed by phi, and then you collect together, then these get the fixed point. So this is like and then you have a periodical point, which is you apply the phi several times and you get back x, and this x is called a periodical point. And then there's another, this is very natural, but the next 2 is a little bit technical, but actually is also very important to understand the dynamical system. One is so-called stable points. What means stable point? Actually, stable point is like you're going back. You think about usually when you think about the dynamic system, you apply the phi, you iterate the phi in the positive direction, which means phi n is always non-negative. But the stable point, actually, you think about the backward. So if a point is a stable point, if you can always trace back which means like x0 is a element of capital X. If usually, because phi is not surjective, so x0 may have no pre-image. But if this element always has the pre-image, and then we say this point actually is the stable point. And there's another notion so-called attractive point. This is a typical notion from the dynamic system. So attractive point actually is you take the intersection of all this, you apply the phi I to x, and you take all the union, and then this is called attractive point. And as a simple exercise, you can show that actually fixed point is included in the periodic point, and you get this inclusion. So you need to, but this is very not so hard to show. So, but in dynamic systems, people curious about when those 2 sets, the later 2, the last 2 sets are coincide. So this is the one of the question. And there's a nice example which show that stable set may not be equal to attractive set. And this is the one of the example due to Gödel. This is not very, I think this is, it's, to me, it's amazing that this paper actually is published in 2010. So I thought that this kind of example should has long history, but the thing that is not so old, so it's very new. So Gödel construct this example, so show that indeed those 2 sets are not equal. And then after that, a lot of people on the complex dynamics, and they have a lot of work continuing this example, because you can get a lot of similar example in their setting, like in complex dynamic. Most of the people cited this example is from the complex dynamics. Let me have a look. Let's say so this example. So the x actually is the point, like I put here. So it's some point. The idea to get something stable is, for this example, the dynamic is from here. Like you start from 1, 0, yeah, you go this direction, you follow this direction. This is the dynamic, the phi, and everything will converge to this line, 0, -1, -2. But you know that for each one here, all these tails are only finite. So no point here will stable. Only the point here is stable. And which means if you think about the stable point, and there's no stable point, because everything will have no infinite many pre-images. But the negative points actually is attractive set. So which means this is not equal. This is empty set and this is not empty, so they are not equal. Maybe just look at this picture, you will see. Because stable point, which means this can have a pre-image infinite many, but everything will end. They're only finite many. So now let me talk about the stability problem in differential field. So the idea actually is quite simple. You just view a differential field as a discrete dynamic system, and where the set is the k, and the self map is just the derivation. So this is, then you can view this pair as a differential dynamic system. And then the natural question is, what are the stable set and what are the attractive set in this setting? This is very. And then also we know that this just you can collect all the CK denotes the constant subfields, and we know that the differential field is can be viewed as a vector space over the constant field, and also the derivation is the linear map. And the first proposition I showed that actually for this setting, for differential field, if you view a differential field of characteristic 0 as a dynamic system, and then the stable set is coincide attractive set. So you don't need to distinguish those two. So you will not get the Gödel's example in this setting. That's the. And then the stability problem is, given an element in the differential field, you want to decide whether the element is stable or not. So more precisely, which means because this is stable is also attractive, which means for each I, f in the intersection of the union, which means f for each I and f, there exists a gi in k such that this is, what does this mean? This means f can be integrated I times, still get the integral, the ith integral of f is still in k. So for each I. So this is exactly what I said, the feeling of the, you can integrate a function infinite time, you still get an element function. If we take k as an element function field, and then the stable just mean you can integrate this function arbitrary terms. So this, I just formulate this in this using this dynamical system language. So, and then the question is, can you characterize all possible stable element function like Liouville's theorem did? Indeed, here I think I have two more slides which is show the main result. The first result we show that actually there is another way to describe the stable elements in differential field. If f is stable, then actually you can show that for this is the nth, but actually the characterization is this one. If f is stable, which you can for each, if and only for each I, the x to the I times f is the one's derivative of another element, which means I reduce this e to the I to the xi, so which is you somehow you translate the stable problem to some parameterized version of the integration problem, because here I is a parameter. You need to show that for each I, this has the solution in K. Another non-trivial result, we show that actually, if you collect all the stable elements in the differential field, sure, this is a linear space over the constant field. But actually, you can show that this is also a module, a differential module over the rational function field, a rational polynomial range. So this is actually the module. And still open problem is that whether this module is free or not. I checked some special case. This is indeed is free, but in general, I don't know how to show that this is free or not. This is still a unsolved problem. And for example, we already know that exponential x is definitely stable because you can integrate this, still get the exponential. And then by this module over the polynomial, you can show that you can multiply this x to the n, you still get a stable. So actually stable element is closed under multiplying by polynomials. This is the meaning of the module. And I also characterize the 3 special class of elementary functions when they are stable. The first class is called rational. We know that any rational function actually is stable in elementary function field because any rational function has an elementary function, antiderivative. But then x to the I must be still a polynomial, a rational function. So rational function is always stable in this field. But a rational function is not stable in rational function field only when this f is polynomial. Another result is if f is a rational function, if tan by log x, and we can also use the characterize when this f, which kind of f such that this is stable. Actually, we can show that f must be a Laurent polynomials. And I think one of my favorite results is following for the exponential function. If f, g both are rational function, and then you can curious about when this is stable. And then the necessary specific condition is f must be a polynomial, and g must be the linear polynomial in x with non-zero a. So this is actually, the polynomial, and we know that exponential of ax plus b must be is very obvious to see that this is a stable. And then as I showed that this has a module structure, so you can always multiply by polynomial, you keep the stability. So the one direction is easy to show, but then from this is stable implies f is polynomial, g is ax, and the proof actually is very technical. I think I spent a lot of time on showing this result, but one day I realized that actually I can use some argument from number theory, which is so-called the infinite descent. So I use the proof by contradiction. If this is not a linear polynomial, I construct a series of polynomial which the degree will decrease strictly. But then you know that for given polynomial, the degree will not drop infinitely. So this is somehow I use the argument like famous. And then in summary, we know some familiar elementary functions are stable. Like you can show that for any rational function, log fx is stable, and the sine, cosine, arcsine, this is are all stable. You can show that. But there are some non-stable elementary functions. For instance, Titan x actually is not stable. You integrate once, you can, but then you cannot integrate twice. So this is not stable. And cotidine, they also have you can only integrate those elements once, but you cannot integrate infinite times. They are not stable. And also I also have some result about a definite power series. Probably I think I have no time, so maybe I can stop here, right, Ronnie?
Yeah, so,
if you are curious, you can. I have slides. Also, I send this to Ronnie, so right. You can.
So we can pause here for a little bit, and then we'll go to the breakout rooms quickly, and then afterwards we can come back and talk about the open problems and other questions. Is that okay?
Yeah, I have. Yes.
All right. So let us thank Shaoshi.
Thanks.
Do we have any questions?
Yeah, actually, I have a question. Sorry.
Go ahead.
Yeah, is that okay? Okay. So I see that Ravi is here. So actually, some years ago, when Ravi was at Rutgers Newark doing his postdoc, we discussed this kind of question, namely, which sub-algebra or subfield, right, of functions are closed under both the derivation and integration. Yeah. It's quite clear that by doing integration, one has to expand over and over, right? Like
yes, right.
Polynomial give you a log, then and a log you have to multiply with other variables. I mean variables, polynomials.
Right.
So so we just went a couple of steps. Then we find that it's pretty complicated. You know,
right.
Of course, we didn't know all this history you mentioned. You know, we didn't know all this work. So my question is that, are these related? It seems to be related.
Yeah, actually, I think when I give a talk at the risk, Georg actually asked me the similar question. So because you are both working on this differential and integral algebra, so because this natural because the differential and the integral algebra is closed under taking derivation and integration. So you will naturally think about which kind of algebra actually is closed under integration. So that's but usually we know the polynomial, but here actually, so as you see in the open problem, what I have obtained, the result actually is very restricted. You see, only for three things, very classic, very restricted class of the function, which I can characterize. This is when this is stable. But for very general question, actually, I still in progress. I don't know how to. Maybe you mean, can we characterize all possible element function? For this moment, I think this is still very far away from. I just starting this dynamical thinking of this. Maybe the dynamical formulation actually is not essential, because actually I realized this kind of dynamical formulation very late. Actually, at the beginning I worked this very intuitively, like think about which kind of function you can integrate after many times, you still get a elementary function. That's kind of very direct thinking. And then I realized that there are a lot of people already in the dynamic system. They already think about this backward dynamics, and then I use their language to formulate the stable set and the attractive set, something like this. And maybe I think this also has some connection with what you have worked on this Lotta-Baxter algebra. Yeah, I think they are especially Georg, I think, told me probably one of my lemma can be used your language to prove. I use very elementary way to prove, but there's a more algebraic way to prove this, like this module result. The all stable things from a module. This is sorry, this result. Probably there's a I think my lemma can be simplified, very technical lemma, but and maybe this can be used more algebraic way to prove. But this is still open. So whether this module is free or not is still open. Seems very natural.
So it's good to think about it.
Yeah, I don't know whether this is free or not. It's a differential module actually. Differential module is also closed under derivation. This is
okay, thank you.
Yeah, but clearly, if you have a two stable element, the product is not stable. This is clear. This we know. This is not algebra. This must be just a module. So this is so.
Yeah.
Any other questions for?
Hi, Sals, can you go to the page 19?
This one.
Yeah, your favorite result.
Yeah.
Why a is not equal to 0?
When a is equal to 0, and then this is like then you see this is always, then this is just a rational function. So this is always stable in elementary function fields. That's why. You
so
mean
it's still true when A is not equal to 0.
When A is
logically
0. When A is 0, this is a constant, right? It's constant, and then polynomial is pure. Polynomial is stable. This is still, I see. Because here maybe I forget the one, because see I have assumption that G is not a constant. That's what.
Okay.
That's what.
I see. That's
okay. Why
That's fine.
actually, if G is constant, then we will not think about this case.
I see. Sure.
And then this case, this will imply that A is not 0.
Oh,
Otherwise, all the argument will not work.
Sure.
Right.
Now I understand. Thank you.
Yes.